Okay, guys, so let's kind of dissect this question here. So you should have some kind of idea about the solution of this question by grading and self-assessing the problem using the answer key that was posted in Google Classroom. Let's kind of go through this here. So part A asks to determine basically how you would give maximum angular velocity. So suppose the rod is more massive than the disk. So that's telling us that we can model the disk as a point particle. Okay, to give the rod as much angular speed as possible, should the student make the disk hit the rod to the left of point C, at point C, or to the right of point C? So point C is the position of the center of mass. Okay, so for part A, we know that we need the disk to hit to the right of part C. So it tells you to explain without using equations. You, of course, can think about the equations to help you come up with the answer, but you don't have to rely on the equations, okay? Or you shouldn't rely on the equations to come up with your solution there. So we know that torque equals R cross F. The force is perpendicular to the rod. So the larger the radius, so as R increases, okay, torque's going to increase. As torque increases, alpha increases, right? Alpha is d omega dt, the change in angular velocity over time. So that means that omega is also going to increase. So as R increases, omega will increase because torque increases. So that's one way in which you can justify part A. Okay, so you could state that if the disk hits at a larger radius, a larger torque would be applied to the rod, meaning larger angular velocity. Another way in which you can answer part A, you could take a look at the conservation of angular momentum. And, okay, obviously you can't use these equations as your answer, but you can use the equations to get the answer. So initially the system has only angular velocity due to the disk, which if it's a lot less massive than the rod, that means that the moment of inertia would be that for a particle, which is mr squared. We know that angular momentum is conserved. Okay, so if angular momentum is conserved, the final angular momentum must be equal to the initial angular momentum. If the particle hits at a larger radius, the initial angular momentum will be larger, meaning that the angular acceleration of the rod after the collision will also be larger. Okay, so if R is larger, the disk starts with more momentum, which means that it'll have to end with more angular velocity. Okay, so if R is larger, starts with more momentum, angular momentum, so that means that it must end with the same amount of angular momentum, which would be larger, so omega would be larger. Okay, so you can't write down the equation as an answer. You have to write down the answer in words, but you can use equations to help you get there. Okay, part B. On the internet, a student finds the following equation for the post-collision angular omega of the rod in this situation. So the equation states that omega is equal to the mass of the disk times x, which is technically the radius at which it hits, times the initial velocity, divided by I, regardless of whether this equation for angular speed is correct, does it agree with your qualitative reasoning in part A? In other words, does this equation omega have the expected dependence as reasoned in part A? So 2 ways to think about this. Honestly, not sure that this is an accurate equation, but that is irrelevant because it doesn't ask you to determine that, okay? Your answer to part A was that as R increases, omega increases. So looking at that equation, you need to determine if the relationship between omega and the radius, the distance in which the disk hits compared to the axis of rotation. Okay, an increase in one would be an increase in the other, is what you stated in A. So does this equation prove that? If you were to increase the radius, x, does omega increase? Yes. Okay, if you increase omega, does x increase? Yes. So the answer is yes. Explanation: if x increases, omega will increase because they are nearly proportional. Okay, so that's the answer there. If x increases, omega will increase based on the equation. Okay, and that agrees with the statement from part A. Okay, moving right along. Part C, another student deriving an equation for the post-collision angular speed omega makes a mistake and comes up with this equation. Without deriving the correct equation, how can you tell this equation is not plausible? In other words, that it does not make physical sense. Briefly explain your reasoning. All right, so there are a few ways to go about this, but first thing you kind of want to look at is omega, and I guess we could take a look at I first. So we know that angular momentum is conserved. Okay, so if angular momentum is conserved, right? So the final angular momentum must stay constant. If omega increases, I cannot also increase. Okay, so for this to stay constant, if one increases, the other must decrease. Okay, so basically, this equation is not plausible due to the conservation of angular momentum. Okay, so the angular momentum must stay constant if I, the moment of inertia, increases, then the angular velocity would decrease so that the total momentum would stay the same. Therefore, this equation is not plausible. Okay, another way in which you could look at it I'm not going to underline that. You can take a look at omega and the mass of the disk. So same kind of thing here. As the mass of the disk increases, omega is going to decrease. Okay, so if mass increases, it's going to start with more momentum. Okay, and it's going to end with greater angular acceleration, or angular velocity, excuse me. So if the mass increases, it's going to start with more angular momentum. So it will end with a greater angular velocity. According to this equation, however, if you increase the mass, the angular velocity decreases. So we know that can't be true. Okay, so 2 ways to think about that. Part D. Okay, so in parts D and E, we're asked to assume that the disk is not much more massive than the rod. But then in the problem here, they give us the rotational inertia about the pivot, which is m disk times x squared. Okay, which is the moment of inertia for a point particle. So not sure why they're telling us that up there. It's a angular momentum with respect to the pivot, which is m times v initial times x. Remember that x is the radius. We're asked to derive an equation for the speed omega in terms of those variables. Okay, so your answer must be in terms of those variables and any fundamental constants like g. Okay, other variables that are not listed cannot be in the expression. So we know that angular momentum is conserved. Before the collision, only the disk has angular momentum. After the collision, the disk rod system has angular momentum. We're told that the rotational inertia is m of the disk times x squared. Sorry, we're told that the angular momentum with respect to the pivot is m disk times v initial times x. Technically, we plug in what they did here, which we should be able to recognize, is that for omega, they plugged in v over x, right? So one of the x squareds canceled. So you had m times x squared, which was the value for I, times v over x, and one of those x's canceled. Okay, and that's where they got that expression from. So that's the angular momentum of the disk before the collision. After they combine, so we'll have I disk plus I rod times the final angular velocity, omega. And we want to solve for omega. We're told that the I of the rod, or sorry, the I of the disk here is m of the disk times r squared. Just blocked it with my ink. But this is I of the disk. I of the rod, we're told in a previous section, is just I. So we're going to substitute in for that here and then solve for omega. Okay, so you have mx squared plus I times omega. We're going to divide both sides by that quantity to get omega by itself. And we find that omega is equal to the mass of the disk times the initial velocity times x, which again is the radius, divided by mx squared plus I. Double checking here, we have the right variables in our response, so no need to simplify any further. That's our answer to part D. Okay, part E says, consider the collision for which your equation in part D was derived, except now the disk bounces backwards off of the rod instead of sticking to it. So it's now an elastic instead of an inelastic equation, or collision. Okay, is the post-collision angular speed of the rod when the disk bounces off greater than, less than, or equal to the post-collision angular speed of the rod when it sticks to it? Okay, so we know here, okay, so you can use equations. It doesn't say not to use equations here, but you might be better off explaining in words. So we know that angular momentum is conserved. Okay, so due to the conservation of angular momentum, the total momentum before and after the disk bounces and collides with the rod must be constant. Okay, if the disk bounces back after the collision, that means that the angular velocity for the disk is now negative. Okay, so the angular velocity of the disk is now negative. The sum of the angular momentums of the objects after the collision must still be constant because angular momentum is conserved. So if the angular velocity of the disk after is negative, that means that the rod's angular velocity needs to be greater. It needs to increase in order for the sum to still be equivalent to the initial momentum. Okay, so if the disk bounces back after the collision, the angular velocity of the disk is negative. So the angular velocity of the rod must increase for the total angular momentum to remain constant. Okay, so our answer here is a bounce off greater than, less than, greater than. Okay, so if the disk bounces back after the collision, the angular velocity of the disk is negative. So the angular velocity of the rod must be greater for the total angular momentum to stay constant.